Cześć, Miecio. Halo, halo.
Halo, Paweł, ja słyszę ciebie, zaraz muszę tylko kamerkę jeszcze.
Cześć. No ja nie wiem, czy oni tam no się włącza, to jakiś dziwny ten Zoom jest, bo taki od razu nagrywa i wszystko.
No właśnie, tam powinienem się... Czekaj, a dlaczego mnie nie pokazuje? Czekaj, kamera,
Bo masz
którą tu...
zasłoniętą kamerę.
Czekaj, ale ja mam inną tutaj.
Ale, no, bo jesteś tylko taki, że zasłonięte tło na
Nie,
czerwono.
muszę inną kamerę zabrać po prostu.
A. To tam widzę, że to
O,
są tam
czekaj,
w Los Angeles, czy skądś tam jest ten facet, tak widzę. No niech wysłuchamy go, co...
A4T.
Wysłuchamy go...
Czekaj.
O, jesteś.
Dobra,
Wysłuchamy
to...
tego gościa, co ma do powiedzenia i zobaczymy, nie?
No, czekaj, muszę coś tu ustawić.
Pięknie wyglądasz. Przystojny,
Czekaj.
młody.
Kurczę, wiesz co, staram się, czy to... Bo tak jakaś...
Spotkanie będzie po angielsku, widzę raczej, bo tam są ludzie z Los Angeles czy coś tam, ale to się dogadamy jakoś, nie?
Zobaczę, gdzie tu postawić tą kamerę. Może
Dobrze
tak będzie
wyglądasz, tam się nie
lepiej.
przejmuj. Podejrzewam,
Dobra.
że bardzo dobrze wyglądasz.
No dobra, nie o
Ładny
to
obraz z
chodzi.
tyłu jakiś monet, czy co to jest z
Dobra,
tyłu?
nie. Teraz zrobimy sobie...
Bo
czekaj, gdzie tu mamy?
ja zawsze podglądam, kto ma co za plecami, pokaż mi swój background, powiem ci kim jesteś, nie? O, Heshman. Okay, hello, teraz już mamy. Let's switch to English, Miecio.
Okej.
Hello, Hesham.
Hello?
Hello, how are you?
Fine, how are you?
Fine.
Where are you? In Los Angeles or where?
Oh, I am in San Jose, California.
Oh,
But where exactly? Which city?
San Jose.
San Jose.
Ah, okay.
No.
I will be there starting from June 25th because I will be hired in San Diego State University for the summer courses.
Excellent.
In San Diego, actually.
Maybe if there is a chance we can meet.
Absolutely, yes. So my
it.
teaching load won't be very high, just one course, so I will have plenty of time there.
Very good.
But in fact, I just rent a room just somewhere in the nowhere because it's cheaper. So it is a valet center, something like that. So 43 minutes actually from the university, but most courses will be online anyway.
Oh, fantastic. We should meet. We definitely should meet.
Absolutely. So
Oh, I see.
great.
So you see, I'm in San Francisco virtually.
You are in San Francisco, I see.
Virtually.
Yes. Virtual. San Francisco.
Yeah, I am at home. This is a product of technology.
Yeah, so we can very easy cheat people, yeah, where we are.
Oh, deep fake.
That's a deep.
No, but at least I assume that you are real, not the deep fake.
Exactly.
That
is not deep fake. But guess what? How do you know I am not deep fake?
Well, I have a feeling that the artificial intelligence didn't catch my stupid jokes, so a real person understand it.
This whole LLM stuff is confusing.
Well, but frankly speaking, I am a computer science guy as well.
Yeah.
But I am very skeptical to the AI, all of those stuffs, because I really prefer the direct contact between people.
Yes. You ask sometimes the same question to different models, you get different answers.
Oh yeah, it's true.
Very strange.
It's true. I just called Marek in a few minutes ago, and he told me that he needs another 5 minutes, so probably he will be with us in a moment.
Oh, fantastic.
And so let's wait with introductions.
We had David Mittling joined us, which is great. How are you, David?
Good. Glad to be here.
Excellent. I am glad too. I am happy to see everybody. The topic of today actually is very interesting, and I will mention this later. We should really build a small team. The whole idea behind this work stream is to build small teams to look into problems with the objective of solving problems and maybe publishing papers in a workshop, in a conference. Maybe if we have resources, have a demo and we can present it in some conferences or OCP, global or local summit. I will mention this. So it is not just a presentation, it is like solving problems. Oh, we got Bijan.
Mhm.
Bijan, the big shot. How are you, Bijan?
I'm good. How are you?
I'm very good. So we are waiting until everybody joins.
Oh
We
my
haven't.
God, it's really a big team.
Yeah, I
Oh.
sent the doodle poll and almost 24 people uh,
Ah.
uh, responded to it, but you can have more based on the topic.
Mhm.
And in addition to this monthly meeting, we can have on-demand meetings, you know. But it is different from, you know, Ahmed is the leader for the whole TAB project, and he runs Wednesday meetings every other Wednesday. The difference between this work stream and the main tab is that here you are focused more on problems and solutions. And I like to hold workshops and publish papers, you know, and especially in good conferences or workshops. So we need to solve problems here. We don't just make a presentation and move on. We need to build small teams to solve problems. Oh,
I agree, absolutely.
Dan joined too. And we have, looking at you guys, you are fantastic. So building small teams and having papers is easy for you.
But you know, again, I will repeat what you just said. How do you know that I am not a deep fake?
I know because I look at you and you cannot be deep fake. Oh, Tara
Hello. Oh,
joined.
Tara.
Connectivity problems.
How are you,
We
Tara?
can see you, we can hear you, everything is okay.
Yeah,
Okay,
exactly.
fantastic.
And we verified already you are not deep fake.
Okay. Oh, it's like all the crap in my lap. 1 second. So my office. Okay, that's better. I'm used to giving talks in my kitchen.
Oh.
So give it maybe 3 more minutes for other
Sure.
people to join. But let me say something. I said it before, and I mentioned to you in email, Tara. The objective of this work stream is really about solving problems. Like today, you will present problems, and we have great people here attending the call. And hopefully, you can find maybe small subset of those who attended, if not all of them, to work on solving this problem with you.
That sounds
And,
wonderful.
yeah, and if we solve this problem, we better publish the solution. Of course, you can write a white paper, but for people, scientists like everybody here, you better publish it in maybe SICOM or ICC, or Globecom, or one of those big conferences, or even good workshops, or even much better, you can even have a workshop in I love to have workshop in SICOM. We've done it before and I loved it because all those networking guys from all avenue of life, they attend the SICOM. So we need to produce results. Of course, if we have resources, we can even implement the solution for demonstration. That is even better. So so it's not just for you, Tara, to make a presentation and we go home, we are done. We have to continue working together to solve the problem that you will articulate and describe today. And I hope this will be okay with everybody.
So I'd love it if people can turn on their cameras, just because I like to see people's faces if possible. I mean, I would love this to be fundamental.
Interact.
Hi, Judith.
Oh, good. And I would like to thank Judy. Really, she is the one who helped us to bring Tara. Judy is a long time participant in all TAB meetings. She is very knowledgeable about the subject matter. And as I mentioned to Judy in the email, I would like Judy, Tara, and everybody else here who's interested to really work on solving the problems that Tara will talk about today. So I think it is, let us wait for 1 more minute and then at 9:05 you can start, Tara.
Sure.
9:05 my time. And as we discussed, Tara, I will be in ICC next week, so I will try to find a time to visit you in Boulder.
Okay, perfect. That would be wonderful.
Fantastic. Thank you very, very much.
I'm gonna get my presentation up.
Hashem, Inflection is also in Boulder if you want to swing by as well.
Oh, excellent. I will. Thank you very, very
Yeah.
much. I love Boulder. I used to work with Cable Labs and in Louisville, and I go to Boulder all the time. They used to have very good restaurants, the Med, but it's
It's-
closed.
The Med's gone, but
It's
there's
gone,
still
you're
some really
right.
good restaurants.
Yeah, I love Med, and I love their bread. It has olives in it.
It's good.
I used to go eat there only bread and olives. It's very tasty.
Just the free bread, please, and then head out. Give a good tip.
So it is 9:05 now, Tara. Go for it. And by the way, based on the discussions and how time goes, Dan, who is co-chairing this workshop with me, he also has an interesting presentation. He may go through it quickly, but again, it is all based on how Tara presentation goes and the question and answer and all of this.
Okay.
So please go for it. Go for
Sure.
it.
So I'm gonna start without slides. So I just to kind of give you guys an idea of where I'm coming from. So I worked for 25 years on optical frequency combs, right? And what these are essentially optical synthesizers that we can use to interface with atomic clocks to be able to derive microwave signals or electronic timing signals, and to do optical synthesis to compare different optical atomic clocks against one another. This is where I really have a lot of expertise. I've been working on the comparison of optical atomic clocks using frequency combs for about 20 years now. And also working on optical atomic clock networks. So I have expertise there. I don't have as much expertise as Judith does. So it's perfect that she's here in case there's any atomic physics questions that I can't answer. She can help fill in the blanks there because I have not built an atomic clock. So, I've worked alongside many people who have built atomic clocks. And so I've gleaned a certain amount of information from them over that amount of time, but I'm certainly not an atomic clock expert. I've worked in quantum networking. I've thought about quantum networks for something like a year and a half. So what we've been trying to do at NIST is we've been trying to kind of unite the expertise between the time and frequency division. So what we have is we have a lot of expertise in terms of timing, synchronization, time and frequency dissemination, optical and microwave synthesis. And what we're trying to do is we're trying to bring those capabilities and that expertise together with people who have a lot of expertise in terms of building single photon detectors, in terms of things like loophole free Bell tests, right? Quantum information science, etc. So I am definitely not an expert in quantum networking. I'm trying, and every time I talk to my collaborator, I try to give him another PowerPoint presentation every time he says that's 60% right. So I'm getting closer. But I always seem to miss something incredibly crucial about these networks, right? I think partly because, they don't really exist, right? And we're trying to develop a network in this that's relatively novel. It was one of the first networks that was proposed actually for quantum networking, but because inherently it has such stringent requirements for stability and for synchronization, people have not really attempted it thus far. So we're trying to bring our expertise from the time frequency community with all this infrastructure and this expertise in quantum information science, and we're going to make our first pass at trying to make a two node quantum network. So, okay, with that, I'm going to talk about what I know best, and I'd love to be interrupted. So, because I feel like it's not as useful for people to just listen to me babble all the time. So please interrupt, because I don't want anybody to get lost. And I do love the idea of making new friends and collaborators. So if you guys stay engaged and if you guys understand, everything's better for me. And I don't understand why I'm not starting on the first page. So this is me. It's so wonderful to see you all. Thank you, Judith, for introducing me to Hesham. Thank you, Hesham, for your incredible enthusiasm around this and for giving me the opportunity to talk about something I don't know about that well. So let's get started with the stuff I know well. So yeah, I work in the time and frequency division in Boulder, and as I mentioned, we're trying to bring time frequency techniques to from that we've developed for atomic clock networks and comparisons to quantum networking. So basics. I don't know, everybody's background, but in case you don't know much about atomic time, the idea is that, what we're going to do is we're going to use a quantum transition, right? An electronic transition within an atom, a transition that is very long-lived, right? So it has a narrow natural line width. And what we're going to do is we're going to use this as a frequency reference or an energy reference or a time reference with which to stabilize these cycles of electromagnetic radiation. This could be in the microwave photons. This can be optical photons. And the idea is that I can create some sort of feedback system that allows me to ensure that I'm on the atomic resonance so that I can create essentially exquisite periodicity, right, in this electromagnetic wave. From there, what I can do is I can define the second as a certain number of cycles of that electromagnetic radiation, right? So currently we have our definition of the second is, many digits, something like 9.1219 gigahertz, right? As an oscillation in electronic hyperfine transition in the cesium atom. Does that make sense to everybody? Pretty basic.
Yep.
Okay. So, oftentimes people don't think about it, but for the most part, when we're building it, atomic clocks, especially optical atomic clocks, most atomic clocks are actually not time references. They are frequency references because they're so complicated that, you need many people to run them. So somebody goes on vacation, someone has a sick child, somebody takes leave. Those systems are not going to run without some amount of interference. And so in the end, what we do is we have banks of something called hydrogen masers. So these are actually the flywheels that we use for defining US time. And what the cesium fountain clock does is it actually just calibrates the drift of that system to bring it on time. But what we also do is we can use, right, this idea of this definition of time, right, in our measurement of frequency. So if I can define the second against the SI second or an atomic transition, then I have a very precise way to measure frequency. So atomic clocks have made amazing gains. So, we have these little black dots, and these are microwave clocks. And what's happened is they've kind of bottomed out at the 10⁻⁻16 level. And part of the reason for that is that if you're working in the microwave domain, you don't have as many cycles per second. You can kind of think about it a little bit as kind of camera resolution. You don't have as many megapixels, let's say. And so if you have like a pixel, which is your error, the number of pixels that you have are going to define your accuracy and resolution for, let's say, a camera. The reason that people go to optical systems is that you essentially, you can have a higher transition frequency by something like 100,000. So it's almost like increasing the resolution of something like a digital camera, right? So if you think of the pixel as a fundamental error, or you can think about it, the hertz as an error, the more pixels you have, the more hertz you have, the better your accuracy, the better your resolution. And if you want to think about it a little bit more scientifically, when we're talking about microwave atomic clocks, what they're trying to do is they're trying to control the microwave cycle at 1 part per million, which is an amazing level of control. With the optical cycle, to reach an accuracy that's 100 times better, you only need to control the cycle at something like 1 1,000th level. Is that right, Judith? I don't have it written down. Can't remember, but
It's within an order of magnitude.
something like that, right? I think that's right. Right? It's like 1/1000th. Yeah, you're controlling it at 1/1000th of a second. So, but what we've seen essentially is that, partly, due to frequency combs, partly due to the fact that, you have these optical atomic clocks, you naturally gain in terms of resolution and accuracy by going to higher frequency. We've seen this amazing improvement in performance. So it's been something like a factor of 25 improvement per decade, which is amazing. So optical atomic clocks have now kind of broken the 10⁻18 barrier. And so they're now pushing towards 10⁻19. which is fantastic. So that's 18 digits of resolution in frequency. So because optical atomic clocks have also demonstrated over and over again that they're, at least 100 times better than the microwave atomic clocks, there's a push now to redefine the second to optical atomic time with a target date of 2030. So what is 1 part in 10 to the 18? I want to motivate this because, quantum networks need better than this. So at least a quantum network that we're building. So, you can think about it from a perspective of time. 1 part in 10 to the 18 means that you're losing 1 second in like 30 billion years, which is insane, right? Or it's equivalent to measuring the Earth-Sun distance with 1/10 the width of a human hair, right? Or something that we do measure is that we can measure the relativistic time dilation shift, right? Or like basically the warping of space-time at a level of a height difference between 2 atomic clouds separated by 10 centimeters in altitude. Does anybody have any questions? You guys are so quiet. No? Does it all make sense? I'm perfectly happy to answer questions.
This group tends to get like riled up towards the end, and someone like poses one question, and it becomes some interesting discussion.
Well, so far you're confirming what you know and what we know, and we match, so we have nothing to say.
Okay, awesome. Well, when something doesn't make sense because I don't know it well enough, explain it, please jump in. So, since I heard you guys are interested in things like time transfer, I'm going to put up, put up some comparison in terms of, where microwave clocks are, where optical atomic clocks are, and where our time frequency dissemination is in this space, right? So we, when we think about things like GPS, this is like very good GPS. Okay, this is the type of GPS that we're using to transfer UTC around the world. So this is much better than what people are going to get for their cars. But it's it takes something like a month to average down across the noise in the GPS link to achieve 16 digits of resolution in frequency transfer. So GPS is not a great way to send around optical atomic clock system signals, right? So if you're thinking about we actually have a global optical atomic clock network, right? GPS is not going to allow us to take advantage of the improved performance of optical atomic clocks. We also have like a hydrogen maser, this is our flywheel that we use for timing. And then the NIST time scale, of course, is, it's an ensemble of these hydrogen masers, so it has better long-term performance. The SI second accuracy is, in the low 10 to the -16 level, so that's 16 digits of resolution on a 9 gigahertz carrier. Where do optical atomic clocks live? So they live significantly better in this world of frequency resolution, right? So, they can give you something like 1 part in 10 to the 16 in 1 second of averaging, right? So you get 10 to the -16 in 1 second. GPS takes a month to get to the same level. So once again, another illustration, not just graphically, but in terms of why GPS isn't good enough for these systems. Right, optical atomic clock accuracy is now pushing past this 10 to the -18 level, but it's basically around there. That's where a lot of the best clocks currently are. And then what I work on is these frequency combs, and what this is optical synthesis, and we can actually do optical synthesis with kind of a higher level of precision, right? Because we're not reliant on an absolute standard, right? This is relative, this is additive noise. So in terms of optical frequency synthesis, if we think about this in the way that we do electronic synthesis, the additive noise is kind of in this, 10 to the -17 levels all the way down to 10 to the -20 in terms of accuracy. So there's enormous capability in the optical domain. So as I mentioned previously, did somebody have something to say? I heard a voice. That wasn't mine. Okay. We have worldwide development of optical atomic clocks, partly because of their capabilities, partly because of their performance, also because of the fact, if we're going to redefine the second to optical atomic time, we need many, many groups contributing, right? This is a democratic system. And because optical atomic clocks currently are harder to operate than microwave clocks, right? We need the manpower to be able to keep things going. So So, you know, we can think about optical atomic clocks for timing, right? Or we can think about them from the perspective of fundamental physics. So I mentioned this idea that these optical atomic clocks operate at these exquisite accuracies and resolutions. And so what we can do is we can use them for tests of fundamental physics. We can use them to better understand our, you know, or look for variations in models around general relativity. We can, you know, at NIST, we're using them to look for dark matter, which feels like a little bit cheaty because nobody knows what dark matter is. But in any case, if dark matter were able to interact with normal matter through the fine structure constant, there's a chance maybe one day we would see it, right? We can also look for things like time variations of fundamental constants. So this is something we've also looked for at NIST. So, you know, if you have two different atomic clocks that are operating at different frequencies because they're in, you know, different atomic systems, the physics that finds their electronic transition is going to be slightly, they're going to have variations in terms of like things like their sensitivity, things like the fine structure constant. That's one of our favorite things to look at. So what we can do is we can do, let's say, periodic measurements of atomic clocks over time to see if we see a drift in the frequency, which might indicate a drift in our fundamental constant. So we can use these systems for looking for, you know, physics beyond the standard model. Another thing that people are using them for is because atomic clocks are soon going to be limited by the fact that we're not going to be able to define the relative height between two different atom clouds, right? Using, you know, that are in different buildings, let's say, because our classical methods to measure the geopotential are going to bottom out about 10 to the minus 19. So what happens is that your atomic clock now turns around and becomes a sensor, right? So one of the, I'd say, faraway applications of atomic clocks is this idea of using them for, you know, relativistic sensors of geodesy at the millimeter level. That's going to be really hard because of the measurement times. And I didn't put this in, but if you want to know more, ask me about it. Currently, you know, if you want to do a measurement of atomic clocks at the millimeter level, it's going to take something like 3 weeks, right? So that's not a very good that's not a very good commercial product.
And Tara, Oliver threw in a paper that just came out today from like the PTB conglomeration of chronometric leveling with their portable clocks.
Okay, thank you. I didn't see it.
It's pretty cool stuff and pretty related to what you're talking about right now. It's good timing.
Awesome. Does anybody have any questions? Is this all making sense? Is this the
Yeah,
direction you want me to go?
So at the end, maybe towards the end, Tara, when you at the end, maybe you can summarize the specific problems that are not
Yes.
solved yet, challenging problem, and we should solve them.
Yes, yes. So we're going to get there. 'Cause I want to get like to this idea of how hard it is to do this because it's going to get harder with the networking. So this is our atomic clock network in Boulder. We have 2 buildings, University of Colorado and NIST. So we have 2 clocks at NIST and we have 1 clock at GILA. And we want to be able to compare these remote clocks. It starts to look a little bit like what quantum networking would look like, right? Because you're going to have some quantum node in one building and a quantum node in another building. And how do you connect these 2 things? And you're going to do it a very similar way. So what we do is we have 2 ways to be able to connect these atomic clocks. We can connect them via optical fiber. This is one of the better ways to be able to transmit frequency information, right? Because, you know, and I'll talk about that in a second. Another way, which is a little bit more advanced, and which is kind of a research project in this, is this idea of sending optical atomic clock signals using frequency combs. So you're actually using the timing between your optical pulses to be able to send timing information remotely over free space using optical signals.
And I think Jamil gave a talk that touched on that a while back. That's in some of the OCP TAP history, if anybody's interested in learning more.
And the performance of these systems is remarkable. I think, you know, they've done this between 2 mountains in Hawaii, and you know, they were able to do it with incredibly low light level. I can't remember, it was like a microwatt or something like that of optical power. So they did a kind of a quantum noise limited measurement in terms of time transfer with frequency combs. But optical fiber is amazing, right? So what is this? Do you guys want to go? Do you guys care about going over atomic clocks at all? Is this interesting? Because the one thing I wanted to bring up is, I mentioned this idea that you have an atom, you have laser radiation, it's stabilized to the atom. You can think about it in terms of transmission. So the atom is transparent when the laser is off resonant, and it absorbs when it's on resonant. So there's a very easy feedback mechanism. One thing that sometimes people talk about it, some people don't, is a really important component to this, which is Fabry-Perot cavity. And what this is basically two mirrors separated by a low expansion glass spacer. And what this acts as is it acts as like a filter cavity for your laser light. And it limits the drift, but it also narrows the line width. And these are passive systems. They require very excellent environmental isolation and control. But, with a commercial system, you can probably achieve something like 0.1 femtometer drift per second on a 30 centimeter cavity. So that's, a part in 10 to the 16 drift in frequency over 1 second. And they're only $70K. You can buy them in Boulder from a handy little business called Stable Laser Systems. But these are going to turn out to be important, at least for our quantum network. So keep those in mind. So how do we send optical signals around? So, if we're sending optical signals through fiber, classical communication people don't care about whether the carrier is messed up, right? People care about dispersion. But what we care about is we care that the ingoing signal and the outgoing signal look the same, right? The big problem is that if we send light through optical fiber, the periodicity of the wavefronts are going to become distorted because of things like temperature, vibration, humidity, etc., right? And so what's going to be sent through is not going to look the same on the other side. But what we do is we can essentially get a two-way propagation. So we can send our light through the fiber. We can reflect back either, just due to a flat facet on the fiber or a mirror, and send this light back. And what we can do is we can measure how much phase errors are added to that signal. We could use that and feed forward to be able to correct the signal. And this has been done for something like close to 20 years. So this is a very well-established technology. They have a huge fiber network in Europe connecting Italy, France, Germany, and the UK. And they can use this to be able to send, optical atomic clock signals and maintain frequency resolutions of 1 part in 10 to the 18 after 10,000 seconds of averaging, which is pretty remarkable.
Do they use White Rabbit for this?
No, they use this technique of optical feedback. So I had it in another slide. I think it's on another talk. I wasn't sure how to blend these things, but essentially you send your optical signal down, it reflects off of B and travels back through the fiber. And you compare your optical signal, the interference between your outgoing signal and your return signal to measure the phase noise, the added timing jitter. And you can use a frequency shifter at the input at A to be able to feed forward, right? So you're essentially making your input signal noisy so that it compensates the noise of the link so the output is perfect. Does that make sense?
Yeah. It's like a two-way time transfer technique. You're just eliminating all the variables and kind of
exactly.
Yeah.
And the thing is that it has much better precision than White Rabbit.
Okay, cool.
And this is something I'd be very interested in this group to understand why this isn't regularly implemented in some of the optical networks I hear about. Because that's one of the complaints I hear from a lot of folks in this group is that you can't control how much stuff is changing over fiber. But in the academic research world Tara and I come from, like, I'm used to being able to do that perfectly and better than White Rabbit could do, as long as it's an easy phase lock loop. Like, you don't even need a second integrator or anything like that.
The one thing
Because
that
of
like makes it
practical-
complicated is dispersion. So what's nice about sending single frequency light is that you don't have to worry about dispersion. We're not AM modulating like a CW laser, right? So if you're sending, I don't know what happens, once you have many different frequency components, but we're going to find out going forward. So, does anybody have more questions about this? Okay, so we have atoms, we have our frequency link, we have these optical cavities, right, which act as ways to make our lasers narrow in frequency and low drift. I talked about two-way optical free space transfer. This is much more complicated, but what we want to use this for in like a place like the United States is the fact that we don't have the same kind of density that they do in Europe, right? We can't, it's not so, and the next national lab is Canada, okay? I don't know how well their clock is doing this far away. We don't have any dark fiber to connect us to Canada so that we can do clock comparisons. If we want to do things like relativistic geodesy, like this idea of being able to do millimeter level resolution in the geopotential, what we're going to do is we need to move clocks around and we need to connect them, not necessarily over fiber networks. And so this idea of using two-way optical free space transfer, which is very similar to two-way GPS, right? But with much better resolution. This would be the way to be able to take advantage of the resolution of optical atomic clocks in remote locations where fiber cannot connect them. But but the loss is amazing. 30 kilometer 80 dB loss, very different system. But you can reach, 10 to the minus 18, right? 1 part in 10 to the 18 digits of frequency resolution in time transfer at 200 seconds of averaging. So this is a phase coherent process, pretty amazing. Okay, so this is what I build, and I like these systems, and I feel like commercial people should know more about them because they're starting to become they're starting to become products. They're starting to become more robust. They're starting to become a little bit less expensive. But what this is an important component for optical clock networks, and for our systems, for our quantum network, this is going to be important as well. Is these frequency combs. And so, what is a frequency comb? A frequency comb is a pulsed laser. It's a mode lock laser system. You could, if anybody has worked in optics, maybe you've heard of TSIAW lasers. Those would be the original frequency combs. And the idea with this is if you don't want to think about this as a complicated system, you can really just think about it as a synthesizer. So you have a box, you put your optical reference in. You could also put in a microwave frequency reference in. And then what it does is that this microwave reference or this optical reference sets the timing of your optical pulses. And you can, if you're using a good reference, you can set the pulse to pulse timing at less than a femtosecond. And because you have pulses means that, the nature of having pulses means that you're going to have, many different frequency components added together. So I'm taking harmonically related modes. They have exactly the same phase. I add all of these up, and what you end up getting is pulses. So this is basically like a microwave metronome. So I can put it in my atomic reference in, and I can get, a microwave timing signal out. So to measure that timing signal, what I do is I put in a photodetector, but this photodetector is only sensitive to the amplitude modulation of this optical signal. And what it does is it creates an electronic series of electronic pulses. And it actually, you can, if you build your system well, the timing in the electronic system can be as good as in the optical domain, which is kind of shocking because there's a lot of distortion in photodetection. So out of this photonic synthesizer, we put in our atomic reference, we plug it in the back. The box looks a little bit more complicated, but that's okay, right? And what you get is you get a harmonic frequency comb in the microwave domain, and you get a harmonic comb in the optical domain. So essentially, we're going to take this reference and we're going to create a bunch of tones that carry the same accuracy and the same resolution as the atomic reference. So this is a fantastic synthesizer. In terms of the microwave signals that you can get out, you can create microwave signals with, part in 10 to the minus 16 timing accuracy at 1 second of averaging. So in green are kind of like the specifications in the RF domain, in black are the specifications in the optical domain. But I don't know what you guys are, whether you're optical people or microwave people. So whatever you're into, I have both. So we have, we can create, 10 gigahertz signals, which are really great for X-band radar. We can also create 100 gigahertz signals. Both of them have exceptionally low noise. So for the 10 gigahertz signal, if you step 1 hertz off the carrier, the noise falls by about 10 orders of magnitude. So this is similar kind of performance to cryogenic sapphire oscillators. And you can get pretty strong power per mode in the RF domain. In the optical, the additive optical noise is actually at 1 second is something like 10 to the minus 18. So it's 100 times better than optical atomic clock performance. But this is residual, not absolute. Atomic clocks produce absolute resolution, absolute accuracy. Does anybody have any questions so far? We're going to start moving into the domain of things I don't know well soon. So this is where I'm going to need your guys' help. So does this make sense?
I did have a question. Earlier you talked about optical frequency synthesis. Is that like adding filters onto it? What exactly is optical frequency synthesis?
So if you look at this box, right, you're putting in, I didn't draw it very well, but you're putting in a single frequency in, right, with my atomic reference up here.
Okay.
I'm putting a single frequency in, and I get something like 1 million optical modes out in the optical domain. And then the microwave domain, it depends on the bandwidth of my photodetector, but maybe I'll get something like 10 to 20 microwave tones out. And from there, I can do some amount of synthesis on those. You know, with this system, I can only change the spacing between the modes at about the 1% level. So there's not a lot of actual synthesis. It's more that I get, you know, I take one frequency and I get 1 million frequencies that represent both the fractional accuracy and stability of that frequency in the optical domain.
I see. Okay, thank you.
Does that make sense? If it
Yes,
does,
it's almost like a DNA, it's like a DNA sample or whatever. You get the DNA, you can recreate the frequency.
to some extent, it's like, yeah, if you want to think about, you know, the frequency reference that's going in is like DNA, and you're replicating that, right? But across different tones, right? So you know, you really can think about it as an electronic synthesizer. I put in my 10 megahertz in the back. And the thing that's different is with a normal synthesizer, you're gonna specify the frequency and you're gonna create that frequency. So I'm gonna create a related tone. It's gonna carry the stability of the 10 megahertz reference, right? But here, what I do is I produce something like 1 million tones that carry the stability of the reference, but I can't move them around.
Got it.
But in the microwave domain, you know, I get these tones and I can use something like a DDS, and then I can actually start to synthesize and I can start to tune. And if you're interested, the second paper here in Laser and Photonic Reviews explains how we do that. So we could do agile synthesis in principle, right? Because we haven't made a machine from something like DC to 100 gigahertz.
And just to interject, another cool application that I think this group would be interested in is using this comb output to then have those define different channels in an optical network. And you can get these channels very, very narrowly spaced, still individually pick them out. The hard part is getting to, you know, write an individual signal on that channel and being able to separate it. Because here they're all permanently connected. If you do something to kind of your reference, it shows up on all of them. But that's an area where people are starting to do like petabyte per second kind of transfer data levels by implementing combs in their optical networks. And this is one of the best ways to get a stable, reliable comb output.
Yeah, and like, you know, this is actually based on a laser design, right? They actually have ways of making these frequency combs with things like EOMs. And what you're doing is you're creating the tones based on driving a modulator with a good electronic signal. So if you take an excellent electronic signal from a good system and you use an EOM to create comb modes, I have a slide somewhere to explain that. What you can do is you can create a tunable system. So then you have a lot of agility, but there's more engineering complexity. And sometimes there's a little bit of a loss of performance, but not much. But then you end up with a system where you really can tune the spacing by as much as you want because you're really driving it with a microwave signal.
What is the cost of a system like this?
If you right now, because they're not that available, I'd say something like 300K. But if you can, this is always the thing, is if you're comfortable with a system, it's easy to build one, right? So, you know, if we build one, it costs us probably about 15K and, you know, a month of work. So they're not, the parts are not expensive. You know, one can buy the oscillator, so the laser itself, and that's maybe 50K. And you can go to a local company, which is Octave Photonics. You can buy some of the, like these waveguide kind of infrastructures where you could Lego pieces together to then create a stabilized system for another 11K. But then the problem is you need a frequency reference.
Okay.
Right. Judith et al. working on.
So I'm biased, but this is basically like what our atomic clock that we offer right now. That's the benefit of going to these optical atomic clocks. Ours have a built-in comb, and you can have those comb outputs. They don't necessarily have all the knobs you would want to implement them in a network for data transfer right now, but that's a problem we would love to work with you guys to solve as well. And that cost it's less than 300K for these clocks. And we're working to rapidly commercialize this comb technology and the whole system here and bring down the cost.
Yeah, because for a long time, you know, there was a patent that was limiting things. So there's only one company really building these. But now that that patent is expired, this is going out into the public domain. And so there's more competition, and hopefully they'll bring down the cost and improve availability and different types of sources. So I like to think of frequency combs as improving basically the versatility of atomic clocks, right? So you have this beautiful atomic clock, but it only operates at one frequency, right? That in itself is not inherently that versatile. So the optical frequency comb basically allows us to synthesize a bunch of optical frequency around that, right? And it allows us to do this over very, very large bandwidths. What I like the optical frequency combs for as well is I'm like, what is it going to do? My slides. Yes, is that allows us to compare different optical atomic clocks. So one of the big problems for us in terms of doing these tests of fundamental physics, in terms of characterizing clocks, which is a big part of NIST mission, is this idea that these optical clocks are kind of built based on how the transitions that you want inside of them, but also the laser availability, right? So there's some, you know, we don't have lasers at all available frequencies. So, you know, people choose atoms partly, atomic transitions partly due to the lasers that are available to access them. And so what this frequency comb allows us to do is it's not only that we're doing synthesis with it, but it acts as kind of like a frequency ruler. So the spacing between the modes is very highly regular, very equidistant at like the 10⁻21 level. So, you know, if you try to think about, you know, the spacing between the optical modes in this frequency comb kind of as markers on a ruler, let's say the centimeter marker on a ruler, you know, the centimeter marker, you can maybe split by a factor of 20, right? Maybe you can resolve things on a ruler at the, you know, 0.5 millimeter level. But in the frequency comb, because of frequency counting techniques, we can split, you know, the spacing between modes at the 10⁻14 level, 10⁻14 level. So we get, you know, millihertz resolution or better, right, between these different frequency markers. So if we're trying to measure different atomic clocks, what we need to know is we need to know how many modes are separating the clocks. And then we need to know like these little difference frequencies, and we can measure these exceptionally well. Also, you know, if I measure this difference between the different modes, this is at a microwave frequency, and this allows me to make this optical spectrum SI traceable to UTC or to the SI second. This one, because this technology ended up being incredibly enabling for optical atomic clocks, this helped win Jan Hall and Ted Hensch the Nobel Prize. Not the Hensch, Ted Hensch, sorry, the Nobel Prize in 2005. So what's also powerful with these optical frequency combs is the fact that they're pulse systems, which means that they have high pulse energy per second, high energy per pulse. And so you can use this actually to convert frequencies. So you can start with something that's in the optical domain, and you can create terahertz signals or mid-IR signals, or even go all the way down to the microwave level, all the way almost to DC. Or you can upconvert. So I can use harmonic generation as a way to create signals to the XUV. And in case you're interested in any of these different ways that people do this, I've put in some references for you. Does anybody have any questions still? Is this all making sense? It is to Judith, but she worked in this for a long time. She knows me well. Okay.
I'd say my only concern is, yeah, making sure we get to the networking part.
Okay, here's the quantum networking part. So this is, you know, and what do I know? My understanding of all of this is that much of the US's spending in quantum was inspired by the amount of work that's been done by China in terms of QKD. So this is quantum key distribution, right? Not only did they do it on the ground, they were able to do it from ground to a satellite to Innsbruck and back, and this really freaked out the world. So there have been a lot of investment in both Europe and the United States, also in Canada, the UK, and other countries, right? In terms of trying to develop the quantum information science within those countries nationally. For the Chinese quantum network, when they're talking about quantum networking, they're mainly talking about the idea of using quantum key distribution for secure communication. But that's not the only application, you know, that one can have with quantum networking. So in 2022, once again, there was a Nobel Prize for Alain Aspect, John Clauser, and Anton Zeilinger, basically talking about communication using entangled photons. And so this is where we're going. You know, for people like me, who are trying to understand the differences between classical and quantum communications, one of the things that stands out the most is that, this notion of having a quantum internet is unlikely to happen, because the notion with classical communication is that you're striving for high data rates, right? And using lots and lots of photons, right? It's all about throughput. Quantum networking is not about throughput, right? It's about entangling single photon pairs, right? The focus is, either on secure communication rather than high data rates, right? Or remote entanglement of things like atomic clocks or atomic sensors or quantum computers, right? So the application is fundamentally different. And we're with quantum networks, we're working with extremely low powers, right? We're doing single photon counting. So we're working in this domain of statistics, right? And so it's a very different world fundamentally. Does anybody have questions about this? My answers are going to start to get fuzzier and fuzzier as we go along. I'm still learning. Okay. So I want to try to draw analogies between the atomic clock network, which is something I understand, to then quantum networking, right? So in atomic clock networks, we have these, this is something that looks like something like this in Europe, right?
I have one question.
Yes.
As you said, that is a completely different application, and I understand that if we have for normal data centers the data throughput, we have a lot of photons, so we will have a lot of noise, and the coherence will happen extremely quickly. And if we are for the application and we sending the single photons, so it looks like we need to have a separate network. So it means that we cannot share the infrastructure. We need to build a parallel infrastructure. Is my understanding correct?
Yes, you need to have dark fiber. So
okay,
you cannot have systems with, typical optical amplifiers. So you can't just have unidirectional optical amplifiers to boost your signal. So, the big problem with quantum networks is that to be able to ensure that things are entangled, to be able to do the quantum measurements that are necessary, entangled nodes, you need very low loss, right?
Yeah.
Which is fine over like 100 meters of fiber, not fine over hundreds of kilometers of fiber, 100 miles of fiber, right? So, the quantum analog to the, EDFA is a quantum repeater. And that's actually what we're going to try to build. So we're going to try to overcome the loss in optical fiber to be able to share entanglement between remote nodes.
So on this repeater, it would be really very easy to lose this entanglement or something like that.
Oh, absolutely. So, I think currently some of the best quantum networks, which are, there are not very many of them, have data rates of like 1 entanglement event per 100 seconds.
Oh, okay.
Okay, just to give you an idea of like our collaborator who understands this better than us says that where they are in terms of quantum networking is at smoke signals.
Yeah. Have we any data about this Chinese network that they exchange the key. They're using this quantum networking for exchange the keys. How many keys and how long these keys could be? How many of these keys they can exchange per second?
I feel like it's kilobytes or something like that. Is that right, Judith? I think it's at the kilobyte level. Isn't it?
It was really low. And then there's also some concern that like QKD is not actually secure, and a lot of the like top level now like being hyped up kind of benefits of it aren't going to follow through because of these low rates. Like if you're only getting one every 100 seconds, that's a lot of information that's being lost. And
Yeah.
that's information other people could tap into or utilize that maybe somehow you're not getting, especially if you're doing free space. Like you're just showering photons down. It's pretty easy to intercept them. So that's a concern for how QKD is going to roll out and if it will actually be able to deliver on the promises it seems to have.
Yeah, and so the idea there is that you have two channels. You have your classical channel, and then what the entanglement is doing is creating the key to encrypt that classical channel, right? And the only way to be able to distribute, you're distributing the key. I mean, I think that the first demonstrations they did weren't even using entanglement, right? But the idea is that the security involved is that if somebody were to eavesdrop, right, they'd interrupt this entanglement between these two states.
They can eavesdrop, but we will know that.
Yes, exactly. So you would measure the eavesdropping. And I think the problem that the NSA has, so the NSA does not like QKD because you can just have the typical thing. Someone go into the lab, hit somebody over the head with a wrench, and break into their computer, right? I mean, this is the big challenge with anything from the perspective of cryptography is that, you know, maybe your link is quantum, but your keystrokes are not on your computer, right? And so, you know, we're not focusing on so much on the notion of cryptography so much as we are on the idea of at least trying to build this network, right? So, you know, if you can at least get the photonic network in place, then you can start to think about entangling, let's say, quantum sensors, entangling quantum computers. That would be something that would be done more locally, maybe within a lab. You know, I mean, people are not going to start doing this, you know, over hundreds of kilometers of fiber. You know, they're going to do them within the building because you know, your cryogenic environment can only have so much capacity for dealing with heat. So you're going to have, let's say, you know, if you're thinking about like the types of chip that Google is building, you know, maybe you're going to have one chip in another chip in different cryogenic environments, and you need to be able to network those atomic clocks to increase the capacity of the number of logical qubits for their system. So this is where something like quantum networking will come to play. You wouldn't do it in the optical domain necessarily, but if you're thinking about things like ion-based quantum computers, this might be a way that you do that. Of course, the big challenge is that you need transduction, right? So you need to be able to shift the frequencies from, let's say, the optical domain to the microwave domain, or from one optical frequency to another optical frequency while maintaining entanglement and doing this at very high fidelity. So I think currently optical let's say transduction is at maybe 45% efficiency. Is that about right? I think that's what's happening at Jilla, right down the road.
It's quite good. I expect less.
It is, and I think in the optical domain, transduction is I don't know. I'm going to make something up, but I think it's close to 75% efficiency. But the statistics necessary, so the maximum loss that you can have, you know, in your quantum measurements to ensure to like make sure that it's truly quantum requires loss that's better than 70%. Otherwise, you cannot be ensured that it's not classical. So, you know, this loss limit of like, I think it's 67%. Is pretty hard for these networks. And so this would be node to node. So going back to this atomic clock network, we need like some amount of phase stability. We need a certain amount of synthesis, right? If we go to these quantum networks, it's going to look something more like this. So you're going to have some central quantum measurement node. You're going to have a bunch of remote nodes that are connected by optical fiber if we're doing this, right? In the optical domain or photonically. And then maybe, you know, you're networking some communication nodes, maybe you're networking some sensors and some quantum computers. So entanglement in the network is, if you're using the photon, is going to leverage internal states of the photon or the network itself. So we're going to be working on this idea of actually entangling paths within the network. So in some sense, we're using the network for actually the entangled state. And what we're doing is we're entangling the number of photons per path. So this is a very different way of doing networking. Much of the quantum networks that exist right now use the internal state of the photon. So they're looking at polarization as a way of distributing entanglement between remote nodes. So there are big challenges in terms of quantum networking, right? You need the loss to be less than 70% to be able to verify that you actually have distributed entanglement. It requires amazing synchronization, right? Because you're launching photons and they need to be able to arrive at the central node and they need to be able to overlap at least the 90% level. So you need synchronization, timing in terms of synchronization kind of at the femtosecond level. And for the network that we're going to build, one of the big problems is that you need phase stability because the network is carrying the entanglement itself. So we need phase stability at the lambda over 100 level, which is insane. So atomic clocks, on the other hand, atomic clocks kind of require timing at the femtosecond level, 10 femtosecond level, but for the quantum network, you need timing at the 10 attosecond level. So that's 100 times better in terms of timing jitter to be able to pull off this network. And that's why this is where these time frequency techniques come in, right? So, we need to leverage these ideas of how do we basically ensure that there's no timing jitter on our distributed single frequency sources. The other big challenge for there's so many challenges. It's so great. So many challenges for quantum networks. The other thing is you need to be able to create deterministic single photon sources. So identically, what people would want to do is they want to press a button and you get entangled photons flying out of some source, right? And you want to do this wouldn't it be great to do this at gigahertz rates? Right. And so if you hear about people talking about things like, quantum dots, the big challenge with quantum dots is it's hard to make two quantum dots operate at exactly the same frequency. And, with things like NV centers, I think they have more control over the frequency, but there can be issues with respect to, collecting photons from these systems. And so these systems have a tendency to create, entangled photons with low rates. So our approach is going to be to use a pulse laser system, right? Because you can get something like 10 to the 9 pulses per second. This, of course, is going to be a frequency comb. Ta-da! So if we go to the simplest node, let's say we're going to try to draw analogies to this atomic clock network. So we have two, let's say, in the future, we want to improve the measurement. I'd say this is very, very far away and a little bit fantasy, but who cares, right? We're going to network atomic clocks to improve the measurement time, right? To be able to do things like geodesy. So, if we're going to network these two clocks, what we're going to do is the way that we'd set it up is we'd use, not necessarily, we're probably going to end up building frequency combs. Right now we're building mud-lock lasers. And what we could do is we could use something called spontaneous parametric down conversion. And so you're basically running time-wise in reverse the idea of frequency doubling, right? So normally you take two photons and you interact them in a nonlinear crystal to create a photon of higher energy. And we're running this in reverse. So we're taking a 775 nanometer photon, we're splitting it into two daughter photons. These photons are not entangled, but they should be identical in frequency. And what we do to create a deterministic source is that we actually would have a single photon detector that would produce one of the pairs, would eat up one of the daughter pairs to let us know that we actually have created a single photon. The thing that's very challenging about all of this is that the efficiencies at which we would create daughter photons would be a 1 in 100 chance. Somebody's not muted.
Today, I want to tell you about the shocking murder that changed your life.
Troy.
Like, someone you mute
The
them.
murder mystery is the next talk.
Okay, yeah. Does this make sense? This started to get into the world of complexity. So the big challenge here, even though we'd be using very, very, very like a high rate sources, right, like a gigahertz, you know, the chances of producing daughter photons is at the 1 in 100 level, right? And that's true for different nodes. So the chances that you get a coincidence between the two at a central node, assuming that the stability is perfect and that the synchronization is perfect, is 1 in 10 to the 4, right? So this starts to be low rate. But if you're creating these daughter, you know, hopefully the chances are that you're trying to do this at 10, you know, 10 to the 9 times per second, there's a chance that you can create something that's like 100 kilohertz rate. And so this is going to be our approach to quantum networking, but there are still additional challenges, right? Is that, you know, if we're trying to, what we're trying to do is we're trying to control the phase between two states in a system. And because the network is part of the quantum state, the length changes in the quantum network can decohere that system or that signal. And so what we need to do is we need to start distributing frequency references to be able to control the phase of remote sources. And so we'd have at our central node, we'd be now once again using these time frequency techniques of using these really high fidelity optical references that would be distributed between nodes to actually be able to lock these mode lock lasers so that we'd have frequency control over them. So yes, and as I mentioned before, you know, we need to do synchronization at like the 10 femtosecond level or femtosecond level. Another thing that I mentioned is the idea that, you know, if we're distributing entanglement across the system, we need to be able to control the phase fluctuations at a lambda over 100, which is something like 100 times better than is required for current clock networks. And I mentioned how great those clock networks are, so that this is going to be an additional challenge. And we've actually demonstrated that over 7 kilometers, lambda over 100 link stability is possible, but it only exists at like microsecond timescales. So that what that does is it limits the amount of time over which you can actually collect statistics to be able to ensure that you've distributed entanglement. And this limits the amount of time that you can use for quantum protocols if this network ever comes into play. And we built identical single photon sources based on erbium ytterbium glass lasers. These are the systems that we use for our frequency combs for comparing atomic clocks. And we've actually shown that you can create very identical sources. So the idea is I would build a source at one node and a source at the other node. Each of them would produce a single photon. And for the network to be entangled, the network has to not know which direction the photon is coming from. And so it needs the photons to be identical to be able to entangle nodes. And that requires that the two photons are actually identical from remote nodes at the 99% level. So that's in frequency profile and time profile. So that requires a lot of control over frequency, but it also requires a lot of control over dispersion. So one of the biggest challenges ultimately, so let's say we can actually build this network. One of the big challenges is that, you know, we're trying to stabilize the link stability, and we're going to require a classical and quantum channel to do that. So the quantum channel is going to, you know, carry these single photons, so less than a photon per optical pulse. So we're launching these optical pulses into these nonlinear crystals, and on average, we're producing less than 1 pulse per, you know, time that we're doing this nonlinear interaction. So they're going to be something like maybe 10 to the 6 single photons per second, which is very, very low optical rates and very, very low optical powers. But we're going to be launching something like, you know, milliwatts maybe of classical light over the same quantum channel to be able to stabilize the link length. But the thing is that the single photon detectors that are used for detecting these single photons bleach pretty quickly. And so we need to be able to have attenuation on that classical signal at the 10 to the 17 level, which seems pretty impossible to me, but we're trying.
Tara, would it be possible to use like either, you know, different orthogonal modes within a fiber to do these things, or to have like a co-fiber or something like that?
Yeah,
so this
starts to get to the interesting part. So, you know, in terms of making those channels separable, polarization isn't going to do it because the length and dispersion is different on the different polarization. So we've actually already tested that. It doesn't work well. You know, it's also hard to make things frequency separable. Because is it Raman? I think it's Raman scattering will scatter enough photons from the classical channel to the quantum channel to potentially overwhelm the detectors. So separating things in frequency is going to be hard. You can use things like multi-core fibers. So you have, one fiber with 2 cores on it, and you can use that to actually send the classical and quantum signals and separate them. That's one option. We're going to be using the brand network, and so the fiber's already been laid. I don't know how hard it would be to lay different fiber. The other idea is that you can, what we're going to try to do is time bin things. So we're taking a CW laser and we're actually chopping it with like a Thor Labs chopper right at the moment, and try to stabilize that signal and then interleave the single photons in between. And then you use another chopper on the other end and synchronize it, so that we're blocking as much of the CW light as possible. And we're also trying to do this link stabilization with very low optical powers. So we've been able to demonstrate that you can, typically we're launching something like 10 milliwatts into a fiber. And at this point, we're launching like 10 microwatts to be able to achieve the same level of stability. And so I'd say that there are enormous challenges in terms of making these quantum networks happen, but I do feel like the time frequency techniques are going to help a lot. At NIST Gaithersburg, they're trying to build something called DCQNet. I think it's going to be impossible because they're using aerial fiber. So they can have something like, I can't remember, it's like 40 nanosecond time differences over the day, which adds enormous length changes, enormous noise. But what they're going to be doing is they're going to be using the internal state of the photon. So they're going to be using polarization as a way to distribute entanglement instead of the network itself, which is less sensitive to link stability. Anyways,
it's a time check that it's 6 after.
It's 6 after 11.
Yeah.
Okay, so I apologize. I didn't think it was going to take that long. I only had 22 slides.
Mm.
But I think that basically concludes my talk. Does anybody have any questions?
So what is like the top level problem? If you could have, folks from industry and globally looking at this, what is one thing that you think would move the needle on quantum networking most? Or that could be built into existing systems to make them more forward compatible?
I think investment into fiber would be interesting, right? That's something where I think people are going to still need physicists in terms of creating these single photon sources, right? I think it's not been decided what kind of photonic system people are going to use to be able to send entangled photon sources or send single photons. I think what people would love is something like quantum dots, but it's very hard to engineer, right? Because they just kind of grow organically, right? So it's hard to be able to engineer the characteristics such that they create identical frequency sources. So that's a challenge. I don't know much about NV centers. Another challenge, let's say if you're using something like an ion. So an ion is a fantastic way to make entangled photons, right? And you essentially can hit the atomic transition and you'll create a photon. But the challenge is collecting it, right? So I'd say one of the big issues with the way that fundamental science is done in general is you're trying to use grad students to engineer systems. And I'm going to tell you, we do this at NIST all the time, and it is not an efficient way to leverage your workforce. Graduate students are not engineers. Wouldn't you say that that's true, Judith? Don't you feel like right? Graduate students are also not electronic engineers. They're not good mechanical engineers. They're not optical engineers, right? So, I mean, the thing that I think the quantum networking community, the optical atomic clock community, especially in academia and in federal agencies needs, is we need help from industry to teach us how to engineer things properly. Because we're not using physicists for what physicists are good at doing. But yes, I mean, what we're trying to do is we're trying to work with companies in terms of optical fibers. So one thing that we're interested in is that with these quantum networks, at least the way that we're trying to do it, and the thing that I've been told that I don't understand is that the reason you want to build a quantum network based on the number of photons per path, so you're entangling the paths of the network, not the photons, is that it allows the network to scale better. So if you're trying to use things like, you have to imagine it this way. I want people to understand how complex this is. So, let's say you're trying to make single photons here. And the most efficient way right now is using like pulse lasers. So you have like a, 1 in 100 chance at this node, 1 in 100 chance at this node. Then you add it, let's make 4 nodes, right? So that now you have 1 in 8 chance of having coincidences. Okay, so the scaling in the networks doesn't make any sense. And then, there's going to be errors, right? Because if you produce 2 photon pairs, your single photon detectors aren't number resolving. So this adds errors to your system. Loss reduces your rates on top of all of this, right? These systems are so complex, right? And then there's this added issue of like, well, this is all, right? This bad scaling, this is assuming you can make identical photon sources, right? And this is not taking into account loss of your fibers. So what happens with loss in your fiber networks is it just reduces the rates of entanglement, right? So you're sacrificing, what we're going to try to do is we're going to try to sacrifice rates for loss. And this is only over like 3 kilometers. And we're going to have significantly reduced rates. And the big hope for us is that we're going to go from, let's say, entanglement rates, which are 0.0, it's like 10 to the -2 to 10 to the 3, right? At best between 2 nodes. But the scaling for these networks are impossibly low. And so that's I think that what would be interesting is from the kind of engineering side is how do you make this practical? Like, what are the practical applications of this? So what we're creating is we're just creating the laid fiber, right? We're not even connecting anything, because to connect things then requires transduction. How do you now distribute entanglement from one optical frequency to another? Because we're going to use telecom photons to send this stuff around, right? So if I want to connect to an atomic clock that has a different frequency, I have to be able to transduce. Right, if I want to connect to
That's a different NIST division.
Yes. So we're just trying to create, the optical fibers to be able to distribute this networking. But then and so inherently, aside from the fact that we can entangle nodes, what else can we do with this? I feel like our perspective around what quantum networking is going to do has to shift significantly if we're going to move away from the idea of secure communications, which is already kind of possible, with QKD, except if you have a wrench to bash somebody over the head over and steal their data from their computer.
So you highlighted a very good set of challenges, Tara, at least 3 of them in the slide before the last one. And you said the middle one, which is a single source of photon, is the most important one, most important challenge we need to tackle initially.
Well, I'd say, yeah, that's kind of like your laser diode. It's your laser diode equivalent for the quantum network, right? This idea of, overcoming loss is the quantum repeater. That's the next one. You need these horrible things, quantum memories.
Yeah.
To be able to store information, to be able to improve the rates. Because the rates are so low. So that's the next thing that, they're coming up with some cockamamie schemes, that the idea of that, if you're only producing, you have a 1 in 100 chance of producing, like a daughter photons here and here, right? How can I improve the coincidence rate? So can I store photons and launch them so that they arrive at the same time, right? So that I can kind of group my statistics instead of having to wait. Because the longer you wait, the less stability you have in your network. It's such a hard challenge. It's a perfect research project, right? Because it seems impossible. There's so many pieces to it. You can publish forever, right? But from the engineering standpoint, right? Yeah, we need to think about fibers in a different way. So we need to think about how do we disseminate signals differently, because that the other big one is how do we separate this classical and quantum channel? It's not as much of I think it's not as much of a challenge for these networks that use polarization, but those networks are going to scale terribly, so from a practical perspective, what interesting thing can we do with very low rates of entanglement between remote nodes?
Good question.
It's not going to be the same stuff that we're doing now, right? This is not about high throughput. This is not about high data rates. It's about, using quantum mechanics to enable things that are fundamentally not possible with classical systems. So this is not the equivalent of a classical network. It is fundamentally different. So that's, that would be the thing for the commercial world, right? Because ultimately, let's say, this becomes possible, right? Just like with the laser. The laser didn't seem impossible, right? Nobody was thinking you were going to use it to make people's skin look better or make people's eyes look better, right? I mean, I don't think that those guys would have come up with the kinds of applications that were possible once this was launched to the public. Once it was released as a technology out there, and that's a question: how can you use these low data rates, low photon powers to be able to do something beyond what is possible classically?
But would it be possible to do high data rates with quantum communication?
That's the thing, is that so if we can create quantum memories, store photons, right? We can try to improve I'd say that, we can improve the coincidences, but I think it's going to be a long way from creating really high data rates because of the fact that, we're relying on low efficiency systems kind of by definition. I mean, you can get more daughter photons if you turn up your optical power, but the problem is then you get higher error rates. So, with these classical systems, they're expecting one photon here, one photon there. If you suddenly launch two on each side, this becomes an error, right? So the other engineering part of it is the photodetectors. And so this is something NIST is pushing on. So they have, but these are cryogenic systems. And what happens is a photon comes in, it heats up the system and it changes the resistance. And this is a way that they detect that a single photon has come in. But it's hard to detect whether two photons have shown up. And there was actually a smart paper that was talking about the idea of using machine learning as a way to be able to modify the way that these detectors detect without changing the actual growth of the circuits themselves, right? Can you have learning models that can look for slight pattern differences between one or two photons, but still these detectors, I think currently operate at rates of a megahertz because they need to be able to get back down to those cryogenic temperatures to be able to detect again. So there's lots of engineering challenges involved, but yeah.
I'd also just pose that another
So
another key bottleneck is just that the quantum computers often take like a microsecond is short in some quantum computation worlds. So often, like even if you send data to a quantum computer, you're gonna have to wait a second or longer sometimes to get information back out.
Yeah,
So-
what I was gonna suggest is that, due to the laws of physics, I think looking at quantum computing as in terms of like data rates and things like that, it's probably the wrong approach. They probably need to think of it more in terms of information rates, right? And so because there's inherently some, I don't know what you want to call it, aspect of, compression, if you will, and a small amount of, quantum information could contain a lot of data, a lot of information.
Or it
Good
can do
point.
something that's fundamentally not classical. So I feel like data rate is not the way to think. We're not sending data, we're distributing entanglement, right? So, you could use that to improve the statistics of measurement. I mean, that's something that NIST thinks about, right? So for things like, atomic clocks, if you want to do things like geodesy, you're not going to wait 3 weeks before you get your answer. This is not a good commercial product. But, if you can use entanglement or you can use different ways to do the measurement, right? And you can shrink that down to a few hours, and then now you've created something that's commercially feasible. It's still not feasible, don't worry. But I'm just as an example, right? So yeah, I think I don't think you want to think about it as data. You want to think about it as opportunity. How can you use, right, entangled nodes to improve opportunities for systems? But rates is not, I don't think it's, not right now, it's not the way to, I wouldn't go there yet.
So we
trying to
have
set-
we have lots of challenging problems. You articulated them very well, Tara, and I actually very good. But now we need to build to find who is interested to work with you, Judith, and others on really addressing these problems. And some of them are research problems, some of them are industry problems. And I know, for example, that David is interested to work on this. In fact, he proposed to have a presentation. He sent me already the abstract and title of the presentation for the next 2 months. And I'm sure others as well are interested. So it will be really great to, I know Tara and Judith now are interested and they are already doing a great job in this area. But I would really love, beside Tara, Judith, and David, if anybody is interested to work on this kind of problems, to send an email to the TAB email list and let us know what you are interested to work on. Because at the end of the day, we need to solve problems, or at least propose solutions and publish whatever we come up with into some form of white papers or a conference or a workshop paper. So I really appreciate if you can send an email to the TAB list, letting us know what you are interested to work on. We have lots of challenges for sure, and there is lots of interesting work here.
And so I put some of these challenges in the chat as well, right?
Excellent.
Detectors, fibers, right? So how do we send signals, photons around, single photon sources, and
Yeah.
use cases beyond like this analogy to classical communication.
I would appreciate, Tara, if you can, but maybe you are not subscribed to the TAB email list. Can you send me an email and I will summarize those issues?
Sure.
And I will send them to everybody, and I will also let you know how you can subscribe to the whole TAB list. This
Okay.
way you can talk to everybody, because we have interesting work here, and I think there is plenty of opportunities to solve challenging problems and even demonstrate solutions.
I wanted to highlight the things that are known, because there's
Yeah.
still, I feel like there's a lot of versatility and a lot of opportunity in those technologies that exist, that work, that are not being exploited yet. And the quantum network kind of, I feel like we're still in this world of fantasy. We're so far away. But I do feel like what I would love people to do is think more broadly beyond communication.
Yes.
People really get stuck on these ideas of rates. It's more
Yes.
like, what opportunities does entanglement enable? What can we, because it's fundamentally different than classical.
Excellent. By the way, IRTF, the research arm of the internet, they have a research group on quantum communications. And that this is really where all these issues are discussed too. Although currently they are only focused on QED and security stuff, but the chairs of this research group are very knowledgeable about the subject matter.
Yeah, and I think security is a great way to engage
Yes.
the military and the government.
Yes.
I think that thinking about opportunities beyond security is where it
Yes.
gets very
Agreed.
interesting,
Agreed.
right? Because that's
Agreed.
what the public will engage in,
Yes.
if something ever comes. But so if people can throw their engineering minds beyond the idea of data rates, beyond the idea of security.
Yes.
We
100%
we
agree.
align.
You guys
Yeah,
can-
OCP thinks the same way. We really focus first on computation, but networking is another high interest level for us, and
Exactly.
sensing and networking and things like that. We try to avoid all those other areas that just are too hard to work with.
Yeah, but we have to go beyond what we are usually do.
Mhm.
Yeah, so we have to move forward. So anyway, let us really, this is a good start. David also will continue the discussion next month. In between, we need to start to work with people in the industry and academia, to work with Tara, Judy, and David and others to start to tackle these problems and provide solutions. This is really what this work stream is all about. solving problems, and publish the solution, even demonstrate it whenever we have the resources. So thank you very, very much, Tara, for excellent presentation. Thank you very much, Judy, for helping us to get Tara. She is very knowledgeable about the subject matter. I'm very happy to have her in this call. And thanks to everybody, and thanks to Bijan for joining. He is the CTO for OCP, so he's our big shot here. and I haven't met him really. I met other people, but hopefully I can meet him soon. And we are looking forward to the presentation from David next month.
And also,
Thank-
if you're open to it, I mean, I understand the time and frequency aspect of things pretty well, but if you want to understand the networking aspect very well, I put the name of our local quantum network expert, Christer Scham.
Oh,
I don't know if I spelt that correctly. I think it might not have a C, but if you know what, I'll
email me with this information, because
he's the guy. He knows all these,
yes,
loophole-free bell tests, right? QKD, all of that stuff he can explain very well. I can only poorly explain the things I've understood from him.
excellent. And we also, by the way, we also have Ahmed, who is leading the whole TAB project in OCP. He has bi-weekly meeting on Wednesday. So we cannot cover everything in this particular monthly meeting. So maybe that expert, maybe he can come and present his stuff in Ahmed meeting, and we can carry on further discussion in this work stream, which will be more like maybe working sessions to address the solutions. Like after Tara presentation, maybe and David presentation, maybe what we'll do next is to have working sessions where people present a solution for the problem, and people can debate the solution and talk about pros and cons and what kind of publications we'll write for each one of these agreed upon solution, because the team has to agree on a specific solution that we all agree to publish for everybody. So thank you very, very much, Tara. Thank you a lot, Judith, for helping us. And thank you, David, for proposing to have a meeting, to have a presentation next month. And I wish you a fantastic day, wherever you are.
Thank you all.
All the best.
Thank you, Tara.
Bye. Bye.
Thank you.
Thanks, guys.
Thank you.
See ya.
Bye.
Thanks, everyone.
Thanks a lot.